Okay, we're going to look at a combinatoric identity. We'll prove it a couple of ways, and we'll look at it in a special way. N choose k is equal to n minus 1 choose k, actually k minus 1, excuse me, plus n minus 1 choose k. Okay, so let's see why this is true. For right now, we don't know it's true. So let's look at n minus 1 choose k minus 1 plus n minus 1 choose k. Remember that nr, n choose r, the top number factorial in the top. It's the difference between the top and the bottom factorial in the bottom, and the bottom number factorial in the bottom, the lower number, the r. So what we get here is n minus 1 factorial divided by the difference between this number and that number, which is n minus k factorial times k minus 1 factorial, plus this number factorial on top, the difference between them, n minus 1 minus k factorial on the bottom, and k factorial on the bottom. Now, we look at the two bottoms, because when you add fractions, you want the bottoms to be the same. For example, we have k minus 1 factorial here and k factorial here. Well, if you have k minus 1 factorial, which is 1 times 2 times 3 all the way up to k minus 1, if you multiply that by k, you will get k factorial. Exactly what we have here. So on the left side, we'll multiply top and bottom by k. Now, let's look at this. This one is 1 less than n minus k. If I multiply by n minus k, top and bottom, in particular, if you multiply this by n minus k, well, just understand that n minus k minus 1, this is 1 times 2 times 3, all the way up to n minus k minus 1. The next number, which we don't have yet, would be n minus k. We'll multiply the left side by n minus k. Well, on the right side, we have 1 times 2 times 3, dot, 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 all the way up to and including n minus k when no values are missing. So that's going to be n minus k factorial. So now, both denominators are exactly the same. Both denominators are n minus k factorial times k factorial. This numerator is n minus 1 factorial times k. And we're adding n minus 1 factorial times n minus k. Now, if you look at this, between this term and this term, the only two terms in the numerator, they both have n minus 1 factorial in common. So we can factor it out. N minus 1 factorial. And what's left over is everything on the top that isn't in red, that is what I didn't have in common. Namely a k, a plus sign, and an n minus k. And the bottom didn't change. It's n minus k factorial times k factorial. But now we're done. Because if you have n and you take away k and you add back k, this is just n. N minus 1 factorial times n is n factorial. So now this is exactly n choose k. It's exactly n choose k. And the reason is the top number is factorial on the bottom, on the top, excuse me. The difference, n minus k, is factorial on the bottom, and the lower number is factorial in the denominator. So we did prove that this is equal to n choose k. That is, I can now remove this question mark and say it's valid. Now, in my opinion, that's a long way to prove this. Here's an alternate way of proving this. You have n objects. Say they're numbered 1, 2, 3, up to n. Let's concentrate on the first one. Okay, I'm going to break up the n choose way. There are ways of choosing k objects from n into two or disjoint pieces. I'm going to break it up into the first piece that does include 1. I am going to include 1. Plus, I'm going to add all the other combinations where I do not include 1. So now, if I'm including 1, that means I have n minus 1 objects to choose from, and my goal is to choose k, but I already chosen the number 1. I already chose one of them. So I need to choose k minus 1 from the n minus 1. Now, I'm not going to choose the 1. So I didn't choose anything yet. So I better choose k. And how many am I choosing the k from? These. Because I'm not going to pick 1. So I'm choosing k objects from n minus 1 objects. And here it is. Here it is. Now, let's look at this. So we proved it again. Now, let's look at why this one people single out. There's many identities that we could have looked at, or that people in the combinatorics look at. This one is pretty famous for the following reason. When you look at the Pascal triangle, you always put 1 at the left and the right. In row 1, there's only 1 entry. Second row, put 1s at both ends. Then, third row, put 1s at the end. But now there's finally something in the middle that we can add. 1 and 1. From row 2 to row 3, we can add something. You can add these. You can add these. Don't forget to put 1s on the end. You can add these and these and these. Don't forget to put 1s on the end. And this table goes forever and ever. And believe it or not, this table is the same as, I guess, 0, choose 0 for the first row. Actually, this is really row 0. This is row 1. It's going to be 1, choose 0, and 1, choose 1. And 1, choose 0 is 1, and 1, choose 1 is 1. And then row 2. You have 2, choose 0, 2, choose 1, and 2, choose 2. And this is 1, and this is 2, and this is 1. Exactly the same numbers. Then you get 3, choose 0, 3, choose 1, 3, choose 2, and then 3, choose 3. Now, let's look at this a little bit more closely. For example, when you add those two, you get this. Okay, that is 2 choose 1 is the same as 1 choose 0 plus 1 choose 1. And if you add 2 choose 0, and 2 choose 1, you're supposed to get 3 choose 1. 3 choose 1 is equal to 2 choose 0 plus 2 choose 1. Now, if you look at this, let's see what's going on. We're going to talk non-math right now. Whatever the top number is, in the sum, they become 1 less. This is 2, they become 1 less. In the bottom, you have one that's the same and one that's 1 less. This is 1, here's the 1 less, and here's the same. 3, the tops went down 1, this is 1, one of them is 1 less, and one of them is the same. It turns out that when you add these two, you get the one underneath. But that obeys the rule. That obeys the rule. N choose K plus N choose K plus 1 becomes N plus 1 choose K plus 1. Now, that does look different than the top one. It does look different from the top one. I admit that. I'm not saying it's wrong. I'm saying that this N choose 1 K plus 1 is equal to N choose K plus N choose K plus 1. Now, if, for example, I call that big N, well, these will be N minus 1. So we have N choose something is equal to N minus 1 choose something plus N minus 1 choose something else. And if, for example, I call that big K, well, then that's also big K. And this is big K minus 1. Well, that's exactly this rule up here. So Pascal's triangle has this coming up all the time. Okay, it just right there in your face. 0 choose 0, nice and boring. 1 choose 0, 1 choose 1. 1 choose 0. You add these, you'll get, not that it's going to matter, but I meant to say 2 choose 0. This is 2 choose 1, not plus, and 2 choose 2. And then 3 choose 0. These two add up to 3 choose 1. These two add up to 3 choose 2. And we end up with 3, 3. 4, 1. These two add up to 4, 2. These two add up to 4, 3. These two add up. This should be 4 choose 0. I'm so sorry. 4 choose 1, 4 choose 2. These two add up to these two add up to 4, 3. And then 4 choose 4. And finally for us, 5 choose 0. These two add up to 5 choose 1. These two add up to 5 choose 2. 5 choose 3. 5 choose 4. Okay. And that pattern is just there all the time. For example, this if I call that n choose k, it equals to the sum of those two, which is n minus 1 choose k minus 1 plus n minus 1 choose k. Here we did choose the 1, and here we didn't choose the first one, or if you prefer, the 7th one. Either we do pick the 7th one, or we don't pick the 7th one. What's the 7th one? Well, we have n objects, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to n. And we're not, either we are going to pick 7 or we're not going to pick 7. Here, these are the number of ways of choosing k objects from n where we did choose the number 7. Plus, these are the number of ways of choosing k objects from n where you don't choose the 7th object or the purple object, one particular object. Now, why does this work for the binomial expansion? Why is x plus y to the n? Why is it n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the 1, plus all the way down to n choose n minus 1, which will then have plus, which would have x, y to the n minus 1, then finally n choose n, and you'll just have y to the n. The reason is, this here means to multiply x plus y by itself n times, plus y times x plus y n times x plus y. Now, how do you get x to the n? Well, there's only, first of all, remember n choose 0 was 1. How do you get x to the n? Or how do you get y to the 0? How do you get y to the 0? Well, when you multiply just the x's. You multiply just the x's. Okay, and you'll get x to the n, y to the 0. And there's only one way of doing it. There's only one way of getting 0 y's. Okay, now, so I explain this one. Now, what if you want to get just one y? Well, one such way of getting one y, well, it's easy to fix, is pick one y, and then the rest pick x's. But there's one thing here. There's many ways of picking one y. You can pick the first y, or you can pick the second y, x, y, and then all x's. Or you can pick the third y, and only the third y. You can only pick the third y. So you multiply x by x times y times x. That will give you x to the n minus 1 times y. The thing is, how many different ways can you do it? Well, you can either pick y to be in the, you can pick your one y to be the first y, or you can pick that one y to be the second y in the list, or you can pick the one y as the third y, or you can pick it as the fourth place, or the fifth position, or the nth position. So how many different ways can you pick one object from n of them? Is n choose 1 ways. And it just keeps plugging along. The next term, which I didn't list, would be x to the n minus 2 y squared. And I claim the coefficient should be n plus 2. And yes, that totally makes sense because you want to pick from these n factors, two y's. Maybe this y and that y. And then everything else x's. So when you FOIL, you do this times this. Well, maybe I shouldn't have underlined that. You do x times that y. So let's make it look like that. You do x times y times x times x. Why did I underline the x's? I hope you get it. You do x times that y times that x times that y, and then all x's to the final one. And you would have gotten n minus 2 x's and 2 y's. And how many ways can you choose those 2 y's from the n? And choose 2 ways. And if you keep going all the way to the end, okay, n choose n, why did the n? Why did n choose n? The answer is kind of obvious, because you only want to get y's. And since there's n terms, and you're going to pick y from each of them, you're going to pick n y's. You multiply y times y times y times y times y, finally times y. That's going to give you, y to the n. And how many different ways can you do that? Well, you have n objects, n y's, and you want to pick all of them. There's only one way of doing it. It's exactly what n choose n equals. This is why the Pascal triangle works. So, to recap, we talked about how this formula that we derived 2 different ways actually comes from the Pascal triangle. Or better yet, that's how the Pascal triangle is built, by adding this and getting that. Adding this to that and getting the number right below the plus sign. Okay, this is how Pascal's triangle works. And we talked about how we could, I want to do this even again. We talked about how we can derive this top formula up here by arguing whether or not we pick the first object or not. We do want to pick k objects from n. I'm not moving away from that. But we're going to do them, we're going to break up the number of ways of picking k objects from n into 2 different scenarios. One, where you do pick the number 1, and the rest where you don't pick 1. I hope you realize that these 2 are never counting the same. These are counting all the number of ways. Suppose there's 80 different ways of picking k objects from n. Well, some of them will have the 1. Maybe 30 of them will have the 1. Well, then the other 50 will not have the 1. Want that to be crystal clear, that when you add these 2, the number of combinations that do have 1 chosen from it, and the ones that where you didn't pick 1, if you add them up, you're gonna get this. Okay, so now, what does go in here? What combination does give you the ones that have the 1? Now remember, you want to ultimately choose k objects from n. Okay, now if you do pick the 1, you only want to pick k minus 1 objects now. And where are you going to pick them from? You're going to pick them from here. Everything but 1. Well, that's 1 less than n. Okay, now you're not going to pick the 1. Well, if your goal is to pick k objects, and you didn't pick the number 1, well, you better pick k objects then. And you're going to pick them from 2 through n, because you're not picking 1. So you're going to pick them from n minus 1 objects. And this is why this sum is really valid. Or, in particular, I meant to say, that's why that equal sign is valid. Okay, that's going to complete this. And if you like this type of mathematics, please subscribe to my channel, tell your friends about it, and expect to see more math videos on topics like this. Please post your comments below. Let me know how you like it. Thank you.